Hi everybody, welcome to another video in Precalculus section 4.1. We study composition of two functions. So we have function f and function g. The composition of f and g denote f a little circle g of x, or we just say f of g of x. The domain of f of g of x is the set of all the x in the domain of g, such that g of x is in the domain of f. Right. So we have a little graph here. So first of all, we have all the x in the domain of g. So the whole thing is that big. However, whatever the x values we have to have the part that is in the domain of f. The g of x has to be in the domain of f. So that's why only the portion of this will be the domain of the composition. We'll see that in the field example later. But for now, let's just find a simple example. Suppose f of x equal to 5x minus 1. G of x is 3x squared. Find f of g of 1. So basically, this is just f of g of 1. So we do g of 1 first. So put 1 in for x of the function g. That gives us 3. Then we can substitute this back in here, and we have f of g of 1, which is 3. And then f of 3, we're just going to put 3 in for x minus 1. So that's going to be 14. Yeah, put 1 in for g of x, we have 3, and put 3 in there, we have 14. Right, simple as now. Of course, you should see this in coarse algebra already. Similarly, g of f of 2, so we write g of f of 2. And we focus on the inside, which is f of 2. So put 2 in for x of the function f. That gives us 9. And then we have g of 9. And then I put 9 in for x of function g. 81 times 3 to 43. Right, so simple enough. Now, the domain of the composition. Now, the domain of the composition of two functions is, once again, all the x in the domain of g and the g of x such that in the domain of f. So pretty much what we have is the domain of g and the domain of the end result. Right. So the domain of, so first we can write as f of g of x. Now in this case we have g of x is the function here. So instead of write g of x, I could write x of 2. I mean x minus 2, sorry. Yeah, g of x is x minus 2. And then the function f of x is x squared plus 1. So I will substitute x minus 2 here into this x. So this is the function. And the x, instead of x here, we're going to have x minus 2. Right, so yeah, we can do that, or we can say f of g of x. The function f is something square plus 1. And now instead of g of x, we're going to have x minus 2. Yeah, so either way, we just have that. Like I said, of course, we can multiply now and simplify. We don't need to do that. Just need to write the domain. All right, so we write domain of g and then intersection with domain of the combination. So domain of G, this will be all real numbers. I mean domain of G polynomial, so all real numbers. So we have the set of all real numbers intersect domain of this function, also all real numbers. All real numbers. Because intersection for all real numbers are all real numbers. Right. Yeah, I could use the bracket, but that's good enough. That's the idea, right? So it's no big deal here. Since both of them are polynomials, the domain will be all real numbers. The next one will be the same, but g of f of x will be g of f of x. Now, the function g is x minus 2. So I have something minus 2. That is the function g. Doesn't matter what inside. That's what we have. Now, f of x is x squared plus 1, so we have just x squared plus 1 here. This one we can simplify easily. It would be x squared minus 1. And the domain will be the same thing. Domain of G intersect with domain. I should not say domain of G. This is G of f of x. So the domain is not G, but it is domain of the inner function or the domain of the second function. And the domain of the composition. The domain of the function f is all real numbers. So let's say we have that. Interval notation. We intersect with domain of G of f, which is polynomial as well. So all real numbers intersect with all real numbers is all real numbers. Right, so we can write just like that. Yeah. So g of f of x. So put f of x into function g. That into x of the function g. Right. More sample. Now this will be more interesting. Suppose that we have the function f of x is x plus 4, 1 over x plus 4, and the function g of x 4 over x minus 3. Find the combination of the two functions. Alright. And then the domain. So first let's find the combination. F of g of x. So we write f of g of x. Right. Now the function f is what? It's 1 over something plus 4. Yeah, there's a lot of way we can do that. Now, we can have just blank inside here. So we can potentially just put g of x. We can just put g of x here if we want to. And here g of x is going to be 4 over x minus 3. And then, yeah, g of x, and then plus 4. Yeah, put g of x into x of f of x. Now to simplify this, we can think of all of them as fraction. Let's think about that. So we can just multiply top and bottom by the denominator. We only have the denominator of x minus 3. So multiply that top and bottom. So when we multiply that top and bottom, we will have x minus 3 on the top. At the bottom, x minus 3 times that. We cancel out. let's just write like this first. I'm going to multiply x minus 3 and then plus 4 multiply x minus 3. Right, so the x minus 3 here will cancel out. We have x minus 3 on top. At the bottom, x minus 3 cancel out, we have 4. That's 4x minus 12 plus 4x minus 12. Right, now we simplify, we have x minus 3 over 4x minus 8. Right, so that's what we have. Now the domain. The domain will be the domain of the inner function and the domain of the whole thing, pretty much. So we say domain equal to the domain of the inner function and the domain of the whole thing. Domain of the inner function g of x is the domain of 4 over x minus 3 intersect with the domain of the whole function of the computation. Right, so yeah, this is not the proper notation, but the domain, when we divide by something, the denominator cannot equal to 0, so we have x not equal to 3 and then intersect the domain here, the denominator not equal to 0, so for x minus 8 not equal to 0, so for x not equal to 8 and x not equal to 2, so x not equal to 3 and x not equal to 2. So the domain, if we put them together, cannot be 2, cannot be 3, so we just have up to 2 and then we skip from 2 to 3 and then 3 to infinity. Yeah, on the left of 3, between 2 and 3, and on the left of 2. On the right of 3, on the left of 2, and between 2 and 3. Right. Now, just want to show you how that could work in the calculator. So let's just put two functions in. Actually just put one function in. I put the inner function first. G of x is 4 over x minus 3. Right. Next, we can type 1 divided by. Now, this x is composed of the previous function, so I go back in variable y1 of x. Right, so that is, put that in x and then plus 4. See if it works. Yeah. Okay. This is the right scale. So this is the original function g of x. X cannot equal to cannot equal to 3, and that is the second function. X cannot equal to 2. So both of them cannot be equal to 2, cannot be equal to 3. And if you want to confirm it, here I will. You see, when I highlight the equal sign, if I hit enter and it shows the equal sign, meaning that it will not graph it. It's like the switch. The equal sign means off and that means on. Now, I will graph the second function, x minus 3 divided by x for x minus 8. So I just want to confirm that these two functions are the same. So the way we do that, I just go back here, all the way back, and I change the parent to something like that. You see, it will not graph the first function because I turned it off. It will graph this function and it will graph this function in this pattern. You see. So this is the combination of two functions. That's what we have. Now we do this by hand, and you see the circle tracing along the graph, meaning that the second function, meaning that this function is the same as the combination of the two functions. Right, of course you can always. I thought it's nice to see that. Right, I'll just back and just do this by hand. Right, now find the combination of g of f of x. The function g is 4 over something minus 3. Doesn't matter what inside the parentheses, that's what the function g is, right? Now inside of that is f of x. So here we can put f of x in here. Yeah. Doesn't matter what inside, but they have to be the same. Right. So we have 4 over f of x is 1 over x plus 4 minus 3. Now, to simplify this complex fraction, I'll multiply top and bottom by the denominator. The only denominator we have here is x plus 4. So do that, I will have 4 times x plus 4 on the top. You can just leave it like that. At the bottom, 1 over x plus 4 times x plus 4 minus 3 x plus 4 yeah, we can just multiply the top. It doesn't matter. For x plus 12, for x plus 16. And then at the bottom, this cancel out. And we have 1 minus 3x minus 12. So we have 4x plus 16 over negative 3x minus 11. Right? The domain will be domain of the inner function, because it has to be defined first. I just write the inner function because we don't have a lot of space here. Right, domain of the inner function f of x. F of x is 1 over x plus 4 intersect with domain of the combination. So this is x not equal to negative 4 intersect with this x not equal to 11 over 3. Of course, we put them together and we just say it's everything but negative 4 and 11 over 3. So the domain of the computation is the domain of the inner function because it has to be defined first, and then the domain of the whole thing, obviously. Right, now, another example. Suppose f of x is equal to x squared plus 4 and g of x is square root of x minus 2. Find the domain of, find the computation and then the corresponding domain. So, it should be easy. That is f of g of x. Now the function f is what? Something square plus 4. That's what the function f does. Now, in here we have g of x. G of x. You can just put g of x like that. So we have g of x square plus 4. Right. Square cancel the square root. We have x minus 2 plus 4. So that's just x plus 2, right? Yeah, so that f of g of x. Put g of x into that. So simple enough. Now the domain will be equal to the domain of the inner function g of x, domain of g of x, domain of the inner function intersect with the domain of the end result. The computation is 2. Now, domain of square root of x minus 2. We talked about this earlier. If we have the square root function or any even root inside of the denominator have to be greater than or equal to 0, right? So we have x minus 2 greater than or equal to 0. And here domain of that x plus 2. X plus 2 is a polynomial. So we just say all real numbers if we want to, or we use interval notation. Yeah, just say all real numbers. Yeah. At this point, if the notation might not be perfect, but you know what it means. It is, yeah. If I want to be precise in that, of course, I could not write like that. X minus 2 greater than 2, so I just say x greater than or equal to 2. And then intersection with all real numbers. Space, sorry. Now, let's focus on the intersection here for a minute. We have a number line. Say number line here. First, we have all real numbers, meaning that it could be anything on that line. And when x greater than 2, greater than or equal to 2, so meaning anything greater than or equal to 2. And here we find the intersection, which means the overlap of the two. And the overlap of the two is going to be from 2 to infinity. So we just say 2 to infinity. So this has to be defined first. G of x has to be defined first, and then we consider what's left of the function. Right. Next, g of f of x, we do the same thing. G of f of x is g of f of x. G, the function g, is the square root of something minus 2. Doesn't matter what that something is. But if it is f of x, then that have to be the same thing, f of x, like that. So I have square root of f of x is that x squared plus 4. And then minus 2, which gives us square root of x squared plus 2. Right, now the domain. The domain of the computation is equal to the domain of the inner function. Domain of the inner function is x squared plus 4 intersect with the domain of the whole thing, which is square root of x squared plus 1, x squared plus 2. Right. So the domain of the inner function and the domain of the whole thing, pretty much. So the domain of x squared plus 4, that polynomial, we can say all real numbers. That intersect with the domain of square root of x squared plus 2. Well, that again, a square root or any even root, we let inside the root be greater than or equal to 0, because if we have negative, it will be imaginary. So move 2 over. And now you see that is true because x squared, the function x squared is like this, is greater than or equal to 0 already. If it is greater than or equal to 0, it's certainly greater than negative 2. Right? So that one is true for every x, because x squared is greater than or equal to 0. Because x squared is greater than or equal to 0, certainly greater than or equal to negative 2. So in that case, any x will work. So domain of square root of x squared plus 2 is all real numbers. Also, all real numbers intersect with all real numbers. If all real numbers they overlap, it's just all real numbers. Or if we want to write in interval notation, will be that. Right. So once again, the domain of the computation is the domain of the inner function and the domain of the computation itself as a function. Right. Next, show that the two computed functions g of f of x and g of f of x are equal. Well, so first we have f of g of x. The function f is 2 times something minus 5. Inside of that we will put the function g of x. The function g of x inside the parentheses, so we're going to put both of them here. 1/2 x plus 5. Now multiply it out. 2 and 1/2 cancel out. We have x plus 5 minus 5. It's going to be x. And then we do the second part of it, g of f of x. Now first the function g is 1/2 something plus 5. Yeah, it doesn't matter what we put in that, in the parentheses. That have to be the same thing here. So just put the parentheses. Okay. Now, if we choose f of x, it is going to be 2x minus 5. So here we have 1/2 2x minus 5 plus 5. Negative 5 and 5 cancel out. We have 1/2 times 2x. 2 and 2 cancel out. We have x. And indeed they are the same. In the next section, when this happened, we say f and g are inverse. of each other, but that's the next section. Right. What we do now is, it is pretty simple. However, in calculus, this is extremely important. We have to be able to see the change, the combination of functions. So how do we write this function as the combination of two functions? Well, that's easy. First, let's put the parentheses around the square root here. So in that case, one function we can split into, one of which square root of the parentheses, and then we can say the parentheses is equal to 3x squared plus 1. Right? So this is how we decompose one function into two. In that case, we can say the second function is 3x squared plus 1, and the first function is square root of something. Yeah, so that's how we decompose a function into two. Right. There's a lot of ways we can do this though. You can write 3x squared plus 1. If you just want to have the parentheses around this, perfectly fine. In that case, we have the square root of a parentheses plus 1, where the parentheses is 3x squared. That's perfectly fine. The second function in that case is 3x squared, and the first function is something plus 1. Yeah, so it depends on what do we choose to be the second function. If we choose 3x squared, then yeah, the first function will follow to be that. So the answer may be more than one. Right, now this, same thing. Just put something in the parentheses. Let's choose the whole denominator here. So we have 1 over something, and that something is equal to 2x minus 5. And then we decompose a function into two. The first function is the reciprocal function, replaces parentheses by x, and the second function is 2x minus 5. Right, so simple enough. Next we have this. Of course, we have the parentheses already, which is good. We have the parentheses cube, and then the parentheses is equal to negative 3x to the fourth minus 2. So we have two functions. Negative 3x, I'm sorry, something cube, right? So just say something cube, let that something be x. And then the second function, the inner function, negative 3x to the fourth minus 2. Right. So it looks simple, but when we get to calculus, this, if you can see how the functions are composed, and that will help you to do some other things later. But that's all I want to cover in this section. As always, thank you for watching, and see you in another video in pre-calculus.